Hi everybody, this is Miss McClellan here to go over notes, IM2 Notes 3.2.1 with you, constant ratios and right triangles. We have two learning goals. One, I will be able to prove that all slope triangles on a given line are similar to each other. And two, I will be able to write down possible reference angles for given slope triangles. This is going to be your first lesson in this textbook's sequence of trigonometry. First problem is 3-68, patterns in slope triangles. Now, in order to determine an angle, such as the angle at which the Leaning Tower of Pisa, you need to investigate the relationship between the angles of the sides of the triangle. You will start by studying slope triangles. Let's locate the graph shown below. Here it is. We're going to try to notice that one of the slope triangles have been drawn for us. And what we are going to do is draw 3 slope triangles on the line. Kind of. Really what we're doing is we're looking at 3 triangles that have been drawn to us. But imagine this is your original slope triangle. You have a slope of up 1 over 5. The equation of this line would be y equals 1 over 5 times x, and the y-intercept is 0, so it's just plus 0. And then the point is that the next triangle is going to have the same slope because it's also created by drawing a right-angled triangle on the same line. So it has a 90-degree angle right here and an 11-degree angle right here. So this is going to be over 2 up 10. And again, we have y equals 2 over 10x, which is the same as 1 over 5x. Moving on, we can just do this over and over and over again. If we go over 15, we have to go up 3. Hopefully you see that we have a constant ratio. These triangles are similar. They are similar by angle similarity. They share a 90-degree angle and an 11-degree angle. And since the triangles are all similar, the slope ratios are proportional. These slope ratios are proportional. And remember, a proportion is these fractions equaling each other. So we have 1/5 equals 2/10 equals 3/15. No matter what triangle we drew from this line, the slope would always be the same. And of course it is, because similar figures have proportional side relationships. So This part D is just asking us to do what we did right there, write those fractions. 3-69. Tara thinks that she sees a pattern in the slope triangles. So she decides to make some changes to investigate whether or not the pattern remains true. First, she asks, okay, well, what if I draw a slope triangle on this line with change in y equals 6? What will the change in x be? Let's go ahead and explore Tara's idea. The triangle is down here. I paused my recording to move the triangle into view. Okay, so the triangle is right here. And the question is, what if I draw a slope triangle this line with change in y equals 6? That's right here. Change in y equals 6. What would the change in x be? Well, let's see. If change in y is 6, then we have our slope is 6 over change in x. And I know it has to be proportional to 1/5. So I can solve that. Okay, I have 6 times 5 equals change of x. So 30 equals change in x. And that's all you have to do. Set up a proportion and solve. This was possible because I was comparing the larger triangle to its similar counterpart part. I know they're similar because we have a right angle and an 11-degree angle, since it's on the same line as the examples above. Okay, part B says, what if change in x is 40? Well, we have change in y over change in x anytime you're trying to calculate slope. So we have change in y over change in x is change in y over 40, and we can set that equal to any of these proportions. I'm going to choose 1/5 because it's got the smallest numbers. And then I simply cross multiply. I have 5 times change in y equals 40. And this time I need to divide both sides to isolate my variable. I end up with change in y equals, 40 divided by 5 is 8. We continue. Part C says, Tara wonders, what if I draw a slope triangle on a different line? Can I still use the same ratio to calculate a missing change in x or change in y value? If you're in person, you'd be discussing this question with your team. You're doing this video, so you're probably doing it on your own. Anyway, the question is, can I still use the same ratio? And let's think. We have 2 things drawn here. This is a different line, and it looks like this line has rise 3.246. So 3.6 by 3.2. Does 3.6 over 3.2 equals 1/5? No. Okay. So just by inspection, the answer is no, because the angle will be different. So the triangles won't be similar. So the corresponding sides won't be proportional. Yeah, if 2 triangles are not similar, their corresponding sides won't be proportional. So we won't be able to set up a proportion. which is what the question was asking if we could do. Okay, next problem, 3-70, changing lines. In part C of problem 3-69, so the previous problem, Tara asks, what if I draw my triangle on a different line? With your team, you would investigate what happens to the slope ratio and slope angle when the line is different. We are going to use the grids below, or I am going to use the grids below to graph the lines described. And we'll use the graphs to answer our questions to respond to Tara's question. Remember that Tara's question is, what if I draw my triangle on a different line? Okay, let's check out the graph of the line y equals 2x, 2/5 x. So that has a y-intercept of 0, 0, and the slope over 2, up 2 over 5, which is drawn right here. What is the slope ratio for this line? Well, it's 2/5, change in y over change in x. And what is that angle? Let's see. It looks like the angle is about 22 degrees. Okay. So far, it looks like if you change the line, maybe you change the angle, but let's see. Now I've got another one. On this problem, we would have dragged the point Q such that we had an 18-degree angle. I've done that for you. Here we have 18 degrees. What is the approximate slope ratio here? Well, it's 1.3 over 4.2, but those aren't really numbers that I'm used to dealing with, so I'm going to do the division on my calculator. Let's see, 1.3 divided by 4.2 is 0.3095, about. So the slope ratio for this line would be about 0.3095 when the angle is 18. When the angle is 18 degrees. Okay, next. This is a problem based on an internet version where we had Desmos activities, and that's why it says drag the movable green points so that the line represents y equals x plus 4. That's been done for us. This line does represent x plus 4. Right? Let me take a look at this. If rise is 2.5 and run is 2.5, then change in y over change in x equals 2.5 over 2.5 equals 1. It looks like my y-intercept is here. B equals 4. Yes, that's correct. The slope ratio for this line appears to be 2.5 over 2.5, which is 1, i.e. it's the slope. The slope angle appears to be, let's zoom in. I'm halfway between 40 and 50 degrees, so it is about 45 degrees. Okay, we're asked now to go back and revise our work for problem 3-69. Does the slope angle depend on the slope ratio? Let's check. 3-69. You know what? We already had the right answer. The slope angle does depend on the slope ratio. And that's because if the angles are different, the corresponding sides are not proportional. And a slope ratio is a relationship of it's a ratio. And the ratios should all be the same for the same triangles if you're the same slope angle. Okay. Let's see, 3-71, testing conjectures. The students in um, Miss Coiner's class are writing conjectures based on their work today. As a team, decide if we agree or disagree, true or false, with each of the conjectures below, and explain your reasoning. First question says, all slope triangles have a ratio of 1/5. This is false. For example, here is a triangle with a slope ratio of 2/5. Let's draw that. I go over 5, 1, 2, 3, 4, 5. I go up 2. Here's the line, and here's the slope triangle, 2/5. Part B. If the slope ratio is 1/5 and the slope angle is approximately 11 degrees, this is true by angle similarity. All of the slope triangles, let me fix this. All of the slope triangles on my 11-degree line have rise over run as 1/5 or 2/10 or 3/15, etc. In any case, if I have a 90-degree angle and an 11-degree angle, the slope ratio will reduce to 1/5. If the line has an 11-degree slope angle, then the slope ratio is approximately 1/5. This is true by angle similarity. Different lines will have different slope angles and different slope ratios. This is true. You only have the same angle if you have the same slope. Period. Okay, we continue. We are already at our summary. So here we go. This is a summary of our learning today. The slope of a line is the ratio of the vertical distance to the horizontal distance in a slope triangle formed by 2 points on a line. The vertical part of the triangle is called change in y, read as change in y, while the horizontal part of the triangle is called change in x. That little triangle means change in. All right, slope can be written as change in y over change in x. The slope indicates both how steep a line is and its direction, upward or downward, left or right. The Greek capital letter delta is often used in mathematics to describe change. Mathematicians sometimes use Greek letters as variables for angle measurement. The most common variable for an angle is the Greek letter theta. And in case you can't tell what that looks like, it looks like this. And it's pronounced theta. Two other Greek letters commonly used are alpha and beta. Beta is pronounced beta. When a right triangle is oriented like a sloped triangle, such as the one in the diagram, the diagram went away, I'll draw it right here. Such as the one in this diagram, change in y, change in x, theta. Such as the one in the diagram, the angle the line makes with the horizontal side of the triangle is called a slope angle, this angle right here. Okay, everybody, I hope you found this useful, and I'll see you next time. Have a great day. Bye.